What's going on, everybody, and welcome to part 3 of the Neural Networks from Scratch series. In this video, what we're going to be doing is diving deeper into, I guess, sort of cleaning this up, but also transitioning from very raw kind of Python list code into using vectors and matrices and stuff like that, which is the actual standard of doing deep learning with really any programming language. So that's what we're going to be getting into. First, I just want to bring up a couple of things. One is I've set up a repository for neural networks from scratch in X. So I'll put a link in the description, but it's also pretty simple, github.com/syntax/nnfsix. I found that a lot of people were saying they were indeed following along in another programming language besides Python. So I set up the following repository, both for if you want to contribute. So if you are following along and you've got each video part and you've been coding it, if you want to share it, you can share it here. Also, if you're trying to follow along in another language and you just want something to reference, you can also do that here. So check that out. Again, I'll put a link in the description. Also, thanks to everyone who has contributed and supported the book. We're almost to like 2,000 total people on the book, which is just crazy. That's really awesome. I really appreciate all the comments and questions, suggestions, the edits, all that stuff in the document. That's all going really well, and to put 2,000 people into the same document can certainly be hectic, and it's been pretty good. So thank you guys very much. So let's go ahead and jump into the code for today. So there's a couple of things that I want to do. First of all, we want to simplify this code, and I'm going to save you guys. You don't have to follow along coding this. I just kind of want to show moving from here to more dynamic code before we kind of ditch at least this. So you can follow along for the first part, I suppose. But anyway, what we're going to say here is weights equals a list, and then basically just copy and paste these into here. So it's going to be a list of lists in this case. And we'll just take this, copy, paste, come down, do this last one here, paste, and then we're going to do the exact same thing for bias. So we're going to say biases, because now it's multiples. We're going to say 2, 3, 0.5. I'll fix my standards there. And then we can delete this, and then delete this code, and boom, I've already actually coded this code. So if you, we're going to be using weights and biases like this soon-ish, but not even really. And in fact, I'm probably going to go back. We're going to code just a single neuron, and then we'll go to the 3 neurons with 4 inputs, all in this video. But we're going to use a lot of the code, so I'm probably going to be editing and undoing soon. Anyway, this is one way that we can simplify and make much more dynamic. So what we're doing here is we're going to zip together weights and biases to start. And if you don't know what zip does, it just kind of combines 2 lists into a list of lists, element-wise. So in this case, the first element of this zipped list, or the 0th element of the zipped list, will be another list of the 0th weight and the 0th bias, and so on. It just combines 2 lists element-wise. So we're going to iterate over that, and then we're going to do input and the weight, and then we're going to zip those together. We're going to say the neuron output plus equals the inputs times the weights, and then at the end, we add the bias, append it together, we can run that, and that is the output that we expected. So yeah, that's a cleaner, more dynamic way of doing inputs times the weights plus the bias for a layer in Python. Now, we're still going to transition to doing this in with NumPy and doing vectors and matrices and stuff like that, but this is a cleaner way, and if you're following along in some other language, obviously the answer is to use loops. So, now, the next thing I want to touch before we get into the NumPy stuff is we're still getting a lot of questions on weights and biases. So I just want to clear that up as quickly as possible. So weights and biases are these knobs that I say we tune, but really down the line it's going to be the optimizer that tunes these values in an attempt to fit to some data. And because we've got thousands or hundreds of thousands or even millions of these tunable parameters, we can fit so many things. But the way that weights and biases are impacting a neuron's output, it's a different way. So you could, in theory, have a neural network. I think it would be hard to have one with just biases, but even that's probably possible for some simple tasks. You can also have a neural network with just weights. Like, you don't have to have weights and biases necessarily, but they're very helpful, and biases are almost never going to like negatively impact anything. So you want to have both. And just real quickly, I just want to kind of drive home, why are these different? So imagine you have some value, and we're going to say some value is, we're going to make this 0.5, and then we're going to say you've got a weight, and the weight will be a 0.7, and for now we'll do the same weight, or the same value for a bias. So in this case, what is a weight going to do? Well, the weight is going to be the weight time, some value times that weight, right? It's a multiplied thing. Oops. Weight. And then what's the bias going to do? So let's go ahead and run that first, actually. So we can see negative 0.35. Now, if we want to do the same thing for bias, let's go ahead and print some value plus bias. Run that, and we get basically 0.2. Hashtag programming problems. Anyway, so we have this obvious floating point issue that's probably most programming language are going to have some issue like that. But anyways, you get the idea. So what happened was we converted from, like, so weight was a multiple of this negative, so it stayed negative. Whereas bias, what bias has done is it has offset the value. So it depends on what you're trying to do, but at some point we're going to get into activation functions, and these are functions that kind of determine that final output before it becomes an input to another layer, or maybe even the final output to your network in general. So what's happening here is they're just doing two different things. The weight is just changing like the magnitude. The bias is actually offsetting it. It's no different than the bias in y equals mx plus b for the equation of a line. So in this case, what we've seen is we could go from a negative to a positive using bias. But we could, of course, go from a negative to a positive using weight, right? We could make this a negative 0.7, right? And we could run that, and wow, we got to a positive. But this would be a problem, because what if we started with a positive value? Well, obviously it becomes a negative at the end. But this whole time, whatever some value was after bias, it stayed a positive value because all it does is offset. So these are just two different tools that help in two different ways, and that's it. So anyways, I think this will make more sense as we especially get into activation functions and like rectified linear. It should be unbelievably obvious what bias can do for you. But anyway, just for now, hopefully you can see that there are two different tools doing two different things. And if we have millions of these little tools that we can sort of tweak, we can change the overall kind of outputs. Now, with that in mind, let's get into transitioning into more real mathematics rather than this stuff. So we're going to get into NumPy now and start talking about vectors and matrices and dot product and all these things. And we're going to start by talking about shape, as boring as that might sound. If you've ever worked with any deep learning frameworks, I'm willing to bet that you have hit errors regarding shape. I know that's one of the most common questions I ever get with just deep learning and like TensorFlow, Keras, all this stuff, is people have a shape error. And understanding shape is the first step to understanding how really the rest of this works. So it's essential we get this understood. So that's what we're going to be talking about now. So the concept of shape is that basically it is at each dimension, what's the size of that dimension. So in this case, we've got a list of 4 elements. This is a one-dimensional list. And because we have 4 elements, that means the shape is just 4. This is also a 1D array, and it's a vector. So a list in Python can be an array with NumPy, and if it's just a simple list, then it's a one-dimensional array in NumPy, and then in mathematics, a list is a vector. Now imagine a scenario where we have 2 lists contained in a list. Right? In Python, we call that a list of lists, or LOL for short. In NumPy, this is a 2-dimensional array because that first list has how many lists? 2 lists. Now each list, how many elements does each list have? 4. Now this is the first time we're kind of showing an example of how arrays have to be what's called homologous. This means at each dimension, they need to have the same size for each dimension. So imagine, in this case, if the second list in this list of lists only had 3 elements. Could we say what the shape is? No, because in one case it's a 2 by maybe 4, and then the other case it would be a 2 by 3. So So it could never be an array if it did not have a homologous shape to it like this one does. So in this case, this is a two-dimensional array. It is also a matrix. And a matrix is simply a rectangular array. So a list of vectors is a matrix. Now again, imagine a scenario where you've got three of these lists of lists contained within a list. What are we looking at? A list of lists of lists, or LOLOL. This shape, because we've got three lists of lists, at the first dimension, we have 3 elements. At the second dimension, we have 2. And the third dimension, we have 4. This is a 3-dimensional array. So finally, the last container type I'll just briefly mention is a tensor. So if you've ever played with TensorFlow or heard of TensorFlow, you might wonder, well, what is a tensor? And then some tutorials might call things tensors. So put extremely simply, a tensor is an object that can be represented as an array. A tensor is not just an array, but in the context of doing deep learning in programming, a tensor is represented as an array. So you will work with tensors in the array form. So just in case you're getting information from other sources and so on, you might be really confused, like what is a tensor? There you go. It's an object that can be represented as an array. So getting into our code again, now that we've learned what vectors and matrices and arrays and how they all kind of go together, now that we've learned that, let's remind ourselves, what are we trying to do here? We are trying to do inputs times the weights plus bias. So bias is a vector, inputs is currently a vector, and weights are a matrix of vectors. So how do we multiply, because that's what we want to do. We want to multiply this vector times this matrix of vectors. How do we do that? Well, the way that we do that is with what's called the dot product. So, or the matrix product, but in terms of NumPy, it is the dot product handles for both of these scenarios. So let's talk about dot product. So to illustrate the dot product, let's say we've got two vectors, vector A and vector B. Now the dot product is you multiply element-wise the values in these vectors and you add that all together. So at the 0th index of A times B at the 0th index plus A firsteth times B firsteth plus A at the second times B at the second. So the main thing to note here is the dot product of two vectors results in a scalar single value. All right, getting back to our code, let's try to employ the dot product, but first we're going to do it just with a single neuron. So the 4 inputs, 1 set of weights, 1 bias, and then we'll do the full layer of neurons. And I'm not just doing this to waste time, I'm doing this to drive home a point about how dot product and matrix product really works, so that when we go and then translate to doing things in batches, you're going to understand. Because if we don't do it this way, I assure you, many of you guys won't understand. I can at least attest personally, I didn't actually understand what was going on until I learned a little more about how this actually works. So hopefully I can save you guys that pain point. So the first thing we're going to do is get rid of this code here, and then I'm going to save a copy of this because we're going to need it very soon. But for now, I am going to reduce weights to just being 1 set of weights, and then biases will actually be 2, and now it's just a bias. And then we are going to do the dot product. So we're going to use import NumPy as NP. If you don't have NumPy for whatever reason, you can pip install NumPy. You might have to do pip3 install NumPy or Python 3.7-m pip install, whatever. You should know how to pip install. If you're having a problem, feel free to leave a comment below, but I kind of expect that everybody following along understands how to install packages, but I'm happy to help you if you don't know. So, so make sure you get NumPy. And to do dot product, it's actually unbelievably simple. So we're going to say output equals np dot dot, and then we want to pass either the matrices or the vectors alone of that we want to do dot or matrix product of. In this case, you might want to say inputs weights and then plus bias, and this will work. We'll run it. So print output. It does work. It gives us that 4.8 that we were expecting to see. But really, we're going to do weights times the inputs. In this case, both of these are a vector. So it doesn't really matter which one comes first. We'll get the exact same answer in this case. But very soon, it is going to matter greatly. So first, looking at this code, doing np dot dot weights inputs plus the bias, let's review what happened here before we go to a full layer. So again, reviewing what just happened, we did an np dot dot weights inputs plus bias. Now what's happening here is when we do that dot product of those two vectors, they're just multiplying element-wise each element at the same index of both of these vectors and then adding all of that together. So just that dot product alone returned to us a 2.8. Then we add the bias of 2.0, and that gives us the final answer of 4.8. So pretty simple to understand, I think, up to this point. And now let's get into doing a dot product with a layer of neurons. Okay, so coming back to our code, let's do a dot product of a layer of neurons. So that's why I went ahead and saved a copy here. So I'm going to copy that, come over here, paste that, and then everything stays the same. Weights, inputs, and then biases, right? And now we will illustrate why weights came first. So let's go ahead and first run that, and we can see we get the output that we, again, expected from seeing this. We've seen these operations already, so what's happening in this dot product shouldn't be beyond you because you've seen it in very raw Python code. But that is the output that we wanted. Now, if originally, remember, we were able to interchange inputs and weights because inputs and weights they were both just a vector. And so the order of two vectors is not going to change the output of the dot product. But now, what is inputs is a vector still. Weights is actually a matrix, right? It's a matrix containing vectors. So this is different. So the first element in this dot product, when you do a dot product with NumPy, the first element you pass is how the return is going to be indexed. So in this case, what do we actually want back, right? We want those outputs. Like, what are we modeling here? We're modeling 3 neurons. How did we know? What was the difference that changed when we wanted 3 neurons? At least before we did the plus bias, so the difference in the dot product. The difference was, well, we have 3 sets of weights. This is how we knew this is 3 neurons. So because of that, because we want things in we want that output to be the values from the neurons. We want this. That's what we want. We pass weights as that first input because we want things indexed by those weight sets. That's what we want. And in fact, if we first pass inputs and then weights, we're going to see this doesn't even work, right? It throws an error. And again, this is probably the start of something similar that you've probably seen before if you've ever worked with any other deep learning library, is you get these weird shape errors. And without a really good understanding of what are the actual atomic calculations that are trying to be done here, you're going to get these and have absolutely no clue. Like, what have I done? So, okay, so converting this back to weights and inputs, if it's not already clear what's happening, basically this first thing is going to be broken down into doing dot products of this and then dot product of this. And by dot products, I mean this times this, right? So this dot this, and then it's going to be this dot this, and so on. It's just going to iterate through this matrix of vectors. So again, let's just run that because I don't like looking at the error. Again, let's visualize what has happened in this case. Okay, so to review what's gone on here, we've got outputs as np.weights and inputs. Let's talk about just that for now. And what's going to happen here is because weights is a matrix of 3 vectors, it's going to do this dot product 3 times. So as you can see, it's np.weights, 0th vector. So weights 0 is a vector of weights. So now we can actually do the dot product that we know and love. And so what's going to be returned to us from doing a dot product or np.dot of a matrix of vectors and just a vector, it's going to return to us in NumPy form. This will be an array of these values that will be the dot product of the 0th weights and inputs, and then the dot product of the 1st weights and inputs, and the dot product of the 2nd weights and inputs. And then after that, all we're going to do is add these 2 vectors together to get our final output values. Okay, so that's the conversion of everything into NumPy terms and more mathematics terms. This is the way that you are going to be seeing the calculation. It's the dot product of weights and inputs plus the bias. That's how all the notation that you're going to see is going to be doing this. So moving forward now, you should understand exactly what's happening there, and then also hopefully be understanding how the dot product in NumPy is actually working, because not only are we going to need to understand how that works when we do a layer, pretty soon we're going to be doing things in a batch. So up until this point, our input data has actually just been a 1D array, or a vector of a single sample. But soon what we're going to be doing instead is passing a batch of these samples, and now input data, rather than just being a 1D array or a vector, is actually going to be a 2D array or a matrix. So hopefully now that we've covered shape and what vectors are, matrices and dot product, and you hopefully have a really good grasp of how that's working, I'd strongly advise you not to leave this video if you don't yet understand, so please ask questions below. Also, hopefully we've cleared up the questions about weights versus bias. They're just two different tools for approximating something. And weights times the inputs plus the bias is similar to the equation for a line, y equals mx plus b, something like that, right? So here's an example where x is your input, y is your output, and now we're going to just be modifying weight. You can see how it impacts the equation for that line. Similarly, as we adjust bias, we can make changes to the line that way. And you can see that by adjusting bias, we're able to graph certain lines that we just simply could not have graphed with just simply adjusting the weight alone. So the differences, as well as the actual benefits and use cases for weights versus biases, become even more apparent once we get to activation functions. You don't necessarily need to know how rectified linear is working. We're going to get to that in a little bit, but you should be able to see, at least visually, that by adjusting weights, there's just a completely different impact than adjusting for bias. And basically bias is going to, at least in terms of our activation function, help determine whether or not this neuron is actually firing at all, and if so, to what degree. Again, right now we're just making up values here. This has no meaning. Soon we'll work with a data set that has a little more meaning, and then when we get once we figure out the basics of neural networks, we'll use a real data set and hopefully have even more meaning. But one baby step at a time. It's such a complicated topic in so many ways. It's very easy to skip over things and gloss over things and get to the quote-unquote sexy part of deep learning. But in order to get there and really understand, you got to go through here. So hopefully you guys are enjoying. Again, the series is in conjunction with the book, nnfs.io. Also check out Neural Networks from Scratch in X. Pretty cool. Also, if you're curious, the person who has done the Scratch variant is Daniel, who's the co-author of the book. He's also the one doing the animations, so if you're really enjoying these animations, shouts out to Daniel. He's also done a short video of programming a fully working neural network in Scratch, the programming language, which is absolutely absurd. I will put a link in the description. You can check it out. It's not too long, and it is absolutely insane. Also, some people have been asking and noting the similarities between the animations and 3 blue 1 brown animations, and that is because we are using the manim package. So this is the package from 3 blue 1 brown. And basically what we've done is we've kind of built a framework, and by we I mean Daniel, on top of 3 blue 1 brown to do the animation. So if you guys are really enjoying the animations, again, shouts out to Daniel. Also, I'm just as excited as you guys are. I think the animations are an awesome addition to the channel. So thanks to 3 blue 1 brown and also Daniel for writing that code kind of on top of it to get this done. So anyway, that's all for now. If you guys have questions, comments, concerns, whatever, you know the deal. Leave them below. Otherwise, I will see you guys in another video.